So we've got a series of excellent plenaries, and this will be followed by a series of talks that have emerged from the road mapping process, and much more of that a little bit later. But first, to open our conference, I'd like to introduce Baroness Brown, who plays a key role on the Committee on Climate Change, chairing the Adaptation Committee. And I think we've all come to understand the importance of adaptation in recent weeks. Baroness Brown is also chair of the Henry Royce Institute Governing Board. So without further ado, I'm delighted to introduce Professor Dame Julia King, Baroness Brown of Cambridge. Julia.
Thank you very much, Neil, and good morning, everybody, and great to see so many of you on this video conference. I'm just going to give you a quick kind of context in terms of reminding you about the scale of the energy transition that we face. So could I have the next slide, please? And then the next slide, please. So just a bit of context then. We passed the Climate Change Act 11.5 years ago, committing us to reduce emissions by 80% from a 1990 baseline. And then almost exactly a year ago, Parliament updated that and said, agreed that we should commit to reaching net zero emissions by 2050. So if we have the next slide, please. It was actually pretty challenging to get to 80%. The key things we need are lots of energy efficiency, lots of electrification, things like electrification of our vehicles, lots of growth in our zero carbon power generation, obviously, to provide that electrification. But even with all of these measures, we end up with quite significant remaining emissions in a number of sectors. And those that are particularly relevant, I think, to this discussion on the energy transition are those sectors of industry, aviation, heavy transport, and heating our buildings. So if I can have the next slide, please. Getting from 80 to 100% doesn't sound like that big an extra challenge. I'm a great one for saying the 80% solution, meaning we're nearly there. But actually, when you look at the kind of difference in pace of reduction in emissions, it actually is quite a challenge over the next 30 years. So the red dotted line is the rough kind of trajectory from getting where we are now, which is the black line coming down in emissions. The red line was getting to 80%. The green line is getting to 100% or net zero. So it's quite a scale up in what we need to do. Can we have the next slide, please? And if we look at what we need to do to get there, well, we need to really get the last emissions out of our electricity system, and we quite likely need some hydrogen to do that. Buildings is an area of real challenge. All sorts of new technology is going to be needed, new insulation materials, and also probably some hydrogen there too. Transport, we may well need some hydrogen for our heavy vehicles. Industry, probably going to need some hydrogen there, but also a bigger drive for electrification, and also changing some of our industrial processes like steel making. In terms of waste, we're going to need to see much more recycling and a real focus on the circular economy. Important things to do in shipping, in aviation, etc. But hydrogen actually becomes a very important part of the picture. Could I have the next slide, please? So just to really kind of imprint on us the scale of the changes we need to make. We've got to, in the next 30 years, we've got to somewhere between doubling and quadrupling the size of our electricity system, probably nearer the doubling, but in some of the scenarios, we get to 4 times as big electricity generation system as we have today. We have to increase the generation from offshore wind by almost an order of magnitude. We have just under 10 gigawatts operational today. We need to get up probably to somewhere between 75 and 100 gigawatts. That's a huge growth in that industry. We've got to start pretty much from scratch a hydrogen industry and grow it to provide the amount of energy that's just about equivalent to our electricity system today. We've got to start from scratch a carbon capture and storage industry. We have some 30 million buildings that need to be converted to low carbon heat. So if we did that on a kind of steady pace, that's 1 million buildings a year over the next 30 years. We've probably got about 250,000 really low carbon cars around in the UK. We have to change over the entire car fleet, and changes in afforestation, changes in the way we use land, changes in our diets. So that is a huge amount of change. We've done things of that magnitude historically, we just haven't done all of those things at the same time, or all of so many things of that magnitude at the same time before, I think. So this really is a big challenge, and it brings with it some fantastic and huge materials challenges. So the little diagram at the bottom just shows the increase in size of wind turbine blades, or of wind turbines, and hence of wind turbine blades. So, you know, people are now making composite blades some 120 to 130 meters long. We've seen almost an order of magnitude increase in the power of wind turbines over a period of individual turbines over a period of less than 20 years, in fact, enabled by applying advanced materials to this challenge. So if I can have the next slide, please. I want to end on the note of saying materials and developments in materials are absolutely key to unlocking this transition and enabling it to occur at speed. So there's going to need to be lots more work on hydrogen. And that beautiful diagram, the beautiful micrograph you saw earlier was from Bristol University and was one of these beautiful nanostructures that we may be able to use for storing hydrogen. Buildings are an area of particular challenge where we're going to need lots of low carbon materials, insulation, fuel cells, heat pumps, new ways of heating and cooling them, and absolutely enormous area of challenge where we really do need lots of innovation. And of course also where building controls will be very important. So again, lots more electronics that will need to be low energy. And indeed, electronics will be something that truly enables energy efficiency, just as lightweighting and new lightweight materials. So ultra efficient electronics, ultra efficient communications are all a key part of this transition. Decarbonizing industry, it's going to mean using hydrogen, but things like low carbon steelmaking, something that the team at Sheffield and others in the Royce Institute are working on. Very crucially, we're going to really need to see a move to the circular economy and looking at waste, but also looking at resource availability. Some of these key elements that we're going to be using in all of these electric vehicles and things, we need to be making sure that we are recycling them continuously and not continually digging up the planet. Lots of materials challenges for transport, and lots of materials challenges in delivering this transformation and growth of our power system, whether that's cleverer composite turbine blades, more efficient photovoltaic. So just one example of the innovation is the work at Cambridge University on coatings for photovoltaics using very, very clever physics to enhance the efficiency of the photovoltaics. And I hope we're going to hear about more of those sorts of exciting developments today. But also, of course, better energy storage, because we're going to need to store the energy from the variable generation. We're going to be able to need to store the hydrogen that we're going to produce. So all of these are absolutely fundamental to delivering this transition. And all of these come from the materials research that people are doing. So it's going to be really exciting to hear today about some of the pathways that are going to be using developments in materials that are really going to enable this energy transition. So final slide, please. Just to say thank you very much for listening, and I'm really looking forward to hearing about the road mapping and the presentations to come. Thank you very much indeed.
Julia, thank you very, very much indeed for that excellent introduction and for setting us up for the conference to come. So next slide, please. And the next slide, please. Thank you. Next slide. Yeah. So in 2019, the UK, as Julia has just been discussing, the UK put into law a target of net zero emissions by 2050. So what this conference is looking at is essentially 4 key areas. But I just want to look at this particular slide here, and the areas that we've chosen to look at, we'll look at residential, energy to supply, transport, and mainly businesses. And they comprise most of the issue that we have to address. I also want to note that we did not address, for example, nuclear energy, wind energy, or batteries, partly because nuclear and wind are mature technologies, and batteries are supported by the Faraday Institute. So next slide, please. So we looked at the future of materials and photovoltaic systems, low carbon methods of hydrogen generation, decarbonisation of heating and cooling, and low loss electronics. And the cartoon on the right shows you where the energy and the electricity goes. Next slide, please. So we looked at 4 topics, and the first topic was the future of materials and photovoltaic systems. Now, photovoltaic's energy potential is over 100 times greater than the UK's electricity usage per year. But currently, photovoltaic supplies only around about 4% of the UK demand. So to meet net zero, we need to increase the number of solar cells by at least an order of magnitude. We need to generate over 50% more power per panel. We need to utilize light from more of the solar spectrum. We need to be able to work in much lower light levels, for example, indoors, and we need to be able to enable carbon neutral buildings. And finally, we need to power electric vehicles and aerospace applications. Next slide, please. The second topic we looked at was low carbon methods of hydrogen generation. Now, fuel cells can generate electricity with absolutely no greenhouse gas emissions. However, they rely upon hydrogen. Currently, around about 95% of the world's hydrogen is generated by steam reforming of natural gas and other fossil fuels at very high temperatures. So can new materials enable green hydrogen production scalable to the terawatt level, or more efficient hydrogen production? And can the devices be much longer lasting for the hydrogen production? And finally, can we encourage the uptake of hydrogen through alternative chemical carriers, such as ammonia? Next slide, please. The third topic we looked at was decarbonisation of heating and cooling. Now, 37% of the UK's greenhouse gas emissions arise due to heating and cooling. Caloric materials and thermoelectric materials can create carbon-free heating and cooling alternatives. But how do we improve the performance, for example, of thermoelectric materials? And can thermoelectrics compete ever on efficiency with other technologies? How do we improve the performance of caloric materials? And we'll hear a lot more about that later. And can calorics replace current gas-based heating and cooling technologies? Next slide, please. Finally, we looked at low-loss electronics. And 40% of, as we saw in the cartoon right at the beginning, 40% of primary energy consumption is electricity, and 30% of all electrical energy passes through power electronics. And that's going to reach 80% in the next decade. 3 to 5% of global electricity is used by computing, and that's predicted to increase by up to 21% by 2030, or 8,000 terawatt hours. So there's a huge, huge opportunity here, but what materials will enable more efficient power electronics? What materials can reduce losses in CMOS? And what materials will enable beyond CMOS technology? And finally, what is the technology readiness of these opportunities? Next slide, please. So we undertook a road mapping process, and the idea was conceived at around September 2019. And we collaborated with the IOP, the Institute of Physics, in October 2019, And we engaged the Institute for Manufacturing to carry out our road mapping process. At the same time, the IOP carried out a questionnaire, and we had 272 responses from a community survey between February and March of 2020. We have a series of online workshops between March and June 2020 to do the road mapping, and today we are launching online the key findings of that. But it's not over yet, because we need to do community refinement. So we're going to come back to you and ask you more questions and ask for your views about the results so far. And then we're going to publish the roadmaps in September 2020. Next slide, please. So we've been busy, and so have you. The roadmap contributors come from around about 170 participants in 26 workshops from 48 organizations. And I must say, I do thank all of you who participated in this. It's made it's been a great event to see how this is coming together. Today, we've got well over 500 delegates who've signed up at least for today's launch. Next slide, please. So there were key findings common to all of the topics that we looked at. The need for infrastructure to transfer technology from lab to prototype devices, national facilities for device metrology and degradation testing, national coordination of industrial and academic research programs, targeted investment from UKRI to unleash the potential of the research, and legislation for the uptake and implementation of low carbon technology. Research materials should be resource abundant and scalable and recyclable. And finally, of course, people, training, PhD programs, PDRA support, and so forth. Next slide, please. So what's the impact of all of this? Well, the impact for the UK will be that it will help us meet our 2050 net zero target, creating new jobs and filling the skills gap, and finally, providing energy security for the UK going forward.